In chapter 3, we're talking about functions, and we're starting to work our way up. A couple of sections ago, we started with linear functions, which is the smallest agreed polynomial function there is. We think of that as a degree 1 polynomial because the highest power on x is just 1. Think about mx plus b. The power on x is just 1. Then we worked our way up to quadratics. Quadratic function has what as its highest power on x? 2. Exactly. But those are really two special cases of something that we call a polynomial. Polynomial functions are functions that have coefficients or numbers out in front of x's raised to integer powers. And so you can't have a fraction up there in the exponent place. And actually, it needs to be positive integers. And so we think about those really as our whole numbers. And so when we think about generically what a polynomial function looks like, now that you know what I've said, the way we can describe a polynomial generally, mathematically, is you're going to have some number, we'll call it a sub n, times x to some nth power, plus another a sub n minus 1, times x to 1 less power. So what's going to happen is our powers on x are just going to decrease. Think about your quadratic. We had an x squared, then an x to the first, and then your x to the 0, which is your constant. So continuing the pattern, a sub n minus 2 times x to the n minus 2, all the way down to, you can have an a sub 2 times x squared, plus an a sub 1 times x, plus an a sub 0 times x to the 0. So that is mathematically, generically, how you write a polynomial. Those a's with the subscripts, those are just your constants that are out front, your coefficients. Those were in our quadratic that let us know whether the parabola opened upwards or downwards. Okay, so you just have values out in front of x's to powers, where those powers on x's are our whole numbers. What we're going to see in this particular section is that if you have your polynomial written in descending powers of x, which we do, n is the highest power, and then they descend down to technically an x to the 0 down here. When you have your polynomial written in descending powers of x, this very first term is super important. And so collectively we call this whole thing the leading term. It's the highest agreed term in your polynomial. The highest power on x, which we label as an n here, is the degree of the polynomial. So the highest power on x is the degree. And if you just want to talk about that number out in front of your leading term, so this a sub n is just a number, we call that our leading coefficient. I don't know that our book does a great job describing these mathematical vocabulary terms here. And so these are going to be the words that I use as we talk about polynomial functions. And so I think it's good just to have it explicitly in front of you from the beginning, so we know what we're talking about. Okay? Don't let that stress you out. I know this looks a little scary with the subscripts and the exponents and all of that, but you know, when we think about something that looks like this, 5x cubed minus 2x squared plus 4x minus 1, that is a polynomial. What is the leading term of this polynomial? 5x cubed. It's the whole thing. If your function is written in descending powers of x, which we went 3, 2, 1, 0, we have our polynomial here. And so our leading term is the 5x cubed. That's your leading term. Bless you. What's the degree of this polynomial? 3, exactly. The degree, see if I can get a different color that y'all can see the difference between. Your degree is the highest power on x. And so the degree of this polynomial that I've just written is 3. Sometimes we'll call this a cubic polynomial because the 3 is the cubic. What is your leading coefficient? It is the 5, exactly. And so the 5 is the leading coefficient, okay? And so while this may look a little bit scary, it's just the way that we generically write the polynomial that can encompass any degreed polynomial, okay? Any questions so far? Good. When you draw a graph of a polynomial is a smooth curve that's going to have some wiggles in it sometimes. The linear one doesn't. It's just a straight line. But we know from our polynomial, the parabola, that we already have seen one with some wiggles. One way you can graph a polynomial is just by plotting points. And so here's just a reminder of what the graph of f of x is equal to x cubed is. When you cube something, you multiply it times itself 3 times. So if I plug a negative in, what's going to come out? A negative, right? So a negative times a negative times a negative is a negative. And so, for example, when I plug a negative 2 into my polynomial, that is x cubed, negative 2 times a negative 2 is a positive 4, but times another negative 2 gives me this negative 8 here, okay? And so over at negative 2, the polynomial goes down to negative 8, which is, somewhere down here. If I plug a negative 1 in, a negative 1 comes out. Negative 1 times negative 1 times negative 1 is negative 1. So that's this point here. Well, 0 cubed is 0. So that's that point there. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. So that's up here somewhere. And so this, what you see in here is the parent function for all cubics. And so this is where you can begin to graph a cubic function. What we'll learn is the higher the degree of the polynomial, then you have a chance of having more wiggles, more ups and downs in your polynomial. Okay. Any questions on graphing f of x is equal to x cubed? A very important feature to recognize when you have a polynomial is what happens at the far ends when you graph the polynomial. I'm talking about the very far left and the very far right of your polynomial. That's what we call our end behaviors. And for polynomials, because it's going to be these smooth curves, for the right and left, you have one of two options. It can either go up to infinity or down to negative infinity on the left, and up to infinity or down to infinity on the right. Okay, those are your only options. We already know what happens when we have our quadratic, our second order. We just learned this in class. Our quiz was over it. If the leading coefficient was positive, the parabola opened upwards, meaning to infinity on the left and to infinity on the right. If the leading coefficient was negative, the parabola opened downwards, meaning to infinity on a negative infinity on both the left and the right. That same thing is true for any even degreed polynomial. So if your degree is a 2, if your degree is a 4, 6, 8, 10, anything that's even, if your leading coefficient is positive, the end behaviors will go to positive infinity. If your leading coefficient is negative, the end behaviors will go to negative infinity. Okay? Now, what did we see over here when we looked at our first odd degreed polynomial? This was a degree 3 polynomial. 3 is an odd number, not divisible by 2. In odd degreed polynomials, your end behaviors will go in opposite directions. If your leading coefficient is positive, your polynomial will start at negative infinity and will end at positive infinity. Okay? If your leading coefficient is negative, it's a reflection of that, so it flips it. It will start at positive infinity and go to negative infinity. Okay? And so this is all summarized right here, although I don't love the way they draw this because it's not telling you what's happening in the middle of the graph. And so I think they do have a bit of an error in there by making it look like it's completely connected. This slide is only describing our end behaviors. And so if you want to summarize this, I'm just going to turn this over and say, when we think about end behaviors, if your n is even and your leading coefficient is positive, your end behavior rises to the left and rises to the right. If n is even and your a sub n is positive, that's what you're going to get. If your a sub n is negative and you have an even degreed function, like your quadratic, the end behavior will fall to the left and to the right. I purposefully am not connecting these in the middle because we're only talking about the far left and far right stretches of our graph, not middle behavior. Okay? If your n is odd and your leading coefficient is positive, it will fall to the left and rise to the right. If your n is odd, meaning your degree is odd, your a sub n is negative, it flips that. It will rise to the left and fall to the right. So that's just a little chart that will help you. It actually provides an infinite amount of information regarding your graph because we're saying what happens is x goes to either negative infinity or positive infinity. Any questions so far? Right. So that's going to be something to keep in mind. Here's the theorem that tells us about the wiggles in our graph. So the total number of peaks and valleys on the graph of a polynomial function of degree n is at most n minus 1. Okay. When you think about peaks and valleys, those are your maxes and your mins, or kind of your mountaintops and your valleys. Think about this. If we had a degree 2 polynomial, that was our parabola. If it was upward opening, we had only one valley. Okay, so n here would be 2, and 2 minus 1 is 1. We know we're going to have that most 1, either peak or valley, not one peak and one valley. Collectively, if we count all the peaks and valleys, it will be n minus 1. Okay. Now, if we think about this cubic here, the basic cubic function, my n is what here? What is my degree? 3. It's a degree 3 polynomial. This says that a degree 3 polynomial can have at most 3 minus 1, which is 2 peaks or valleys. How many do you see in this? It's actually 0 because it continues to climb. It's more smooth like that. There's no real peak and no real valley here. Okay? There are 0 peaks and valleys in this cubic. But that's okay because this theorem says at most. It doesn't guarantee you that there will be exactly 2 on a cubic. It says there could be at most 2, meaning there could be 0, 1, or 2 peaks or valleys, okay? But not 3, not 4. Similarly, the number of x-intercepts, remember our x-intercepts are of the form where x is some value, y is 0, values that cross the x-axis or touch the x-axis. The number of x-intercepts on the graph of a polynomial function of degree n is at most n. So a degree 3 polynomial could cross the x-axis 3 times, or 2, or 1, or 0. Okay, it doesn't say exactly n, but at least lets you know what the maximum possibility is for the graph. So just kind of looking at and thinking about the prior slide and the things we've talked about, when we look at this figure in letter A, we have f of x is equal to x cubed minus 4x plus 2. So let's just think about all the different bits of notation that we've already talked about. N is our degree, which is the highest power on x. What is it for this one? It's 3. We need to know whether that's even or odd, and it's odd. What is my leading coefficient? The number in front of x cubed. It's 1. Remember, it's that implied value right in front of the x cubed. It's a 1 in this case. 1 is positive. At that point in time, we can look at our end behavior chart, and we see that n is odd, so we're in this column, but a sub n is positive, so we know our end behavior is going to fall to the left and rise to the right. Okay? And you see that happening here, falling to the left and rising to the right. Okay? N is 3. Remember, when we think about peaks and valleys, we know that this is at most n minus 1. If n is 3, 3 minus 1 is 2. We're going to have at most 2 peaks and valleys. And if we count those, we see that we see exactly 2 here. When we think about peaks and valleys, this is what we're talking about, where it starts to increase and then it decreases, or vice versa from there. And we know that we can have at most 3 x-intercepts. And we do have 3. We have 1 right here, 1 right there, and 1 right there. Okay. Questions so far on that? Just kind of deconstructing what we've seen in the prior slides. Looking at B, the degree of this polynomial is what? It's 5. Our highest power on x is this 5 right there. So that's our degree. 5 is odd, so automatically I know my end behaviors are going in opposite directions. The leading coefficient of this one also happens to be 1. There's an implied 1 in front of the x to the 5th. If it's odd and positive, which is the same thing we had before, it's going to fall to the left and rise to the right. Peaks and valleys are less than or equal to n minus 1, at most n minus 1, so that's 5 minus 1, which is 4. Let's see that we've got that. We have exactly 4 peaks and valleys on this one. Our graph crosses the x-axis exactly 5 times, so we're still in alignment with all the things that were on the prior slide. Everyone get down what we had written. Not to bore you to death, but let's look at something that's a little bit different. Here are in C, we have 1.5 x to the 4th. The 4 is the highest power. This is an even degreed function. When your highest power on x is even, you know that your end behaviors will go in the same direction, either up or down. My leading coefficient for this one is the 1.5 that's out front. Since my n is even and my a sub n is positive, the 2 end behaviors are going to go to positive infinity. So if you think about this graph or this chart that we made earlier, when n is even and a sub n is positive, it's going to rise to the left and rise to the right, rising there and rising there. Okay. For peaks and valleys, I know this is going to be less than or equal to n minus 1, which is 4 minus 1, which is 3. I do have exactly 3 peaks and valleys here. And as far as my x-intercepts, this will be less than or equal to n, which is 4. And this one's the one that's different. Remember, it can be less than or equal to 4, so 2 counts. because it could be 4 or 3 or 2 or 1 or 0. So that one's an okay graph. Last one here. Not to necessarily go through all the things, but n is what here? 6, very good. 6 is even. My a sub n, the leading coefficient, is -1. So we have 6, which is even, and -1, which is negative, so my n behaviors will go down to the left and to the right there. Okay. Maximum peaks and valleys are 6 minus 1, which would be 5. And so here, when we think about peaks and valleys, there's a peak and there's a peak. It's kind of hard to tell whether that's a valley or not, but I think we can probably count it as a little valley there. And so we can see that the peaks and valleys there are just 3, but that's less than or equal to 5. We're good. Crossing the x-axis only at 2 places, but that's less than or equal to the 6 possible total that we could have. Okay? So just deconstructing these graphs just a little bit, thinking about the words that were on the pages before us. Any questions? Good. Just as I said earlier, when you graph a polynomial, the graph of a polynomial function is a smooth, unbroken curve that extends forever to the left and right. When x is large, the graph resembles the graph of its highest degree term and moves sharply away from the x-axis. That's really talking about our end behaviors there, either going to positive infinity or negative infinity. Okay. This takes us to graphing. But the one thing I feel like our book does not do well here that helps us when we graph is to talk about multiplicities. And so I'm going to add some information here that will help us with graphing. So if you have a polynomial that you can write in factored form, let's say x minus 3 to the 4th times x minus 2 cubed times x plus 1 squared. Okay? You don't want to do this, but if I made you multiply all of this out, you would actually have a 9th degree polynomial. Okay? So you would have your leading term would be x to the 9th power. I'm not going to make you do it, don't worry. Okay? Where do I get the 9? If I add all of the exponents here, because if I were to take x to the 4th times x cubed times x squared, remember when you have your exponent rules, when you take a base to a power and you're multiplying, you just add those exponents. So that's x to the 4 plus 3 plus 2, which is x to the 7 plus 2, which is 9. Okay. My power, highest power on x will be x to the 9th, so my degree is 9. Any questions on where that came from? To get your degree, you can think about ignoring the numbers that are inside grouped with x for just a minute. Because if you were to multiply this all out, at some point in time, you will have the x to the 4th times the x cubed times the x squared. That's going to give you your highest power on x. Any questions on that? All right. Then if it's in factored form, you can find your leading coefficient. Let's just say that I had a -2 out here. Then that would give me actually my leading term would be -2x to the 9th. Okay, so that my a sub n would be a -2. So at this point in time, I know that I've got an odd degreed function with a leading coefficient of a negative, which would tell me that my end behavior would rise to the left and fall to the right. We go back to our little chart that we made. If n is odd and a sub n is negative, this is what your end behavior is going to look like. Okay. Now, the next thing that's important to think about is our x-intercepts. So to find our x-intercepts, you're going to take your function and set it equal to 0. You're actually going to be thrilled that you've got your factored version of this, because when you've got your function in factored form, you literally just have to think about taking each one of the factors and setting it equal to 0. Okay. This function will equal 0 if x minus 3 is 0, because I'll have a 0 times something that's not 0 that's going to give me 0. This is our 0 product principle. If I add 3 to both sides, I know I have an x-intercept at 3. If I add 2 to both sides here, I have another x-intercept at 2. If I subtract 1 here, I have an x-intercept at negative 1. Any questions on how we got that? Okay. Now remember from our slide right here, it said the number of x-intercepts on the graph of a polynomial function of degree n is at most n. So if I were to graph this thing, I know that I could have at most 9 x-intercepts. I only have 3. Okay, but that's okay, right? Because it could be 9 or 8 or 7 or 6 all the way down to 0 x-intercepts here. Okay. Then the last thing that we want to talk about, and this is the reason why I'm showing you this example, is something called the multiplicity. Once you know what your x-intercepts are, then it's good to know what your multiplicities are. Your multiplicities, these are the powers outside of each of your factors. Okay? If your multiplicity is odd, anyone knows what happens at that x-intercept? Anybody remember this from another class? It's going to cross. So the graph will cross the x-axis at the corresponding x-intercept. If your multiplicity is even, I've heard different ways of describing this. Touch and turn around, or a bounce, whatever way you like to say, but the graph stays on the same side. So if it was negative on the left side of the x-intercept, it stays negative. If it was above the x-intercept, meaning positive on the left side, it will stay positive. And so the graph stays on the same side. And so let's just use the word bounce. Touch and turn around, bounce. I've even heard give it a little kiss, and so kisses and runs away. So whatever you want to think. Okay, so let's think about the multiplicity. Where am I going to get the multiplicity for x equals 3? X equals 3, that x-intercept came from this factor here. Okay? Its multiplicity is the power associated with that factor. So the multiplicity for x equals 3 is 4. Any questions on where that came from? When we think about our multiplicity, what matters is if it's even or odd. 4 is even, so that tells me that my graph will bounce at 4. Okay. What is the multiplicity for x equals 2? It's this 3. It's the power associated with the factor x minus 2. It's 3, which is odd. When the multiplicity is odd, the graph will cross at that x-intercept. Multiplicity on negative 1 is this 2 back to even, which is another bounce. When the graph comes to you in factored form like this one, there's not a whole lot of math involved. We've not had to do any crazy math. It's just a matter of knowing all these pieces. But here's the deal. Let's start by graphing our x-intercepts. And I'm not going to get a perfect graph, but it's going to be a sketch of a graph, which is going to show a lot of the important features. Graphing your x-intercepts. I have an x-intercept at 3. I have an x-intercept at 2. And I have an x-intercept at -1. So that's where I'm going to start my graph. Now I'm going to use my end behavior. So step 1, start with x-intercepts. Step number 2, think about your end behavior. My end behavior says from my leftmost x-intercept, my graph rises. So you need to start with your x-intercepts to know where to start applying the end behavior. Does that make sense? Good. Then it says from my rightmost, it's going to fall. Any questions so far? Now, without knowing specific y values, at -1, what happens? It bounces or stays on the same side. Since it was above on the left, it stays above on the right. And if you wanted to find your y-intercept, that could give you a little bit more information, but it's not super important. But we're still playing dot to dot, so even though I've bounced, got this smooth little valley down there, I'm going to rise, but then I have to come back down to hit my next one. Okay. That is my x-intercept of a 2. At 2, what happens? My graph crosses. So it's going to cross, but it's got to come back and hit my next x-intercept. And if I've done things right, my puzzle pieces fall together. At 3, I needed a bounce. It was below on the left, so it stays below on the right. So if you do everything correctly, your puzzle pieces fit together nicely. For polynomials, there should be no holes or jumps or breaks in your graph. Okay? Any questions on this example? If you understand this polynomial, you can graph any one in factored form. Okay? So that's our next slide. Nothing quite so drastic, but I wanted to show you something with some higher power so we could talk about evens and odds. So I want you to think about what we just did and try letter A here. So the directions say graph each of the polynomials, and here we've got our first polynomial. You need to think about end behavior, which means degrees and leading coefficients. Think about your x-intercepts and their multiplicities. That tells us whether we're going to cross or bounce. Okay, then you put all that information down on your page, and you've got a nice sketch of your graph. Feel free to work in groups if you'd like, or with a partner. Let me know if you need some help. Anybody want me to put this example back up on the screen? Okay. So you should have the one in your notes that you're working on. And here's so this is like an x to the first times an x to the first times an x to the first. So first question is, the degree of the first of that polynomial is what? It's going to be 3 because it's an x times an x times an x, okay? Yeah, sure.
I just added there just to say if there was another that one kind of added, like, had I not added that -2 out front, then it would have just been a 1. The leading term is x cubed, the leading coefficient is yes. You're welcome.
So I I added that -2 just to make a point, but if there's nothing out front, remember it's that implied 1. So just knowing these few little facts, you can graph a 9th-degree polynomial like we just did without much stress. How you doing? Anybody want to come do it up here on the camera? No brave souls? All right. All right, let's talk about it. We'll work on the last 2, and that should wrap up class for us. Keep losing my pens. All right. So, when we think about this polynomial, if I cover up the 3, the -4, and the 1, what do I have? X times X times X. And so my leading term is just X cubed. And if you want to be specific, you could go ahead and say it's 1X cubed. Okay? So my N is 3. My A sub N is 1. 3 is odd, 1 is positive, so my N behavior will fall to the left and rise to the right. Did you get that far? Great. My x-intercepts, they'll come from saying x plus 3 is 0, x minus 4 is 0, or x plus 1 is 0. Subtracting 3 from both sides, I'll have an x-intercept at -3. Adding 4 to both sides to the second one, I'll have an x-intercept at 4. And subtracting 1, I'll get a -1. Any questions so far? Good. The implied power outside every one of these groupings is a 1. And so all multiplicities are 1, which is odd. So it's going to cross at every single x-intercept. Any questions on that? Good. So here we get our graph. I have x-intercepts as far left as -3, as far right as +4. So at -3, at -1, and +4. I know from my leftmost x-intercept it's going to fall. From my rightmost x-intercept it's going to rise. And I know it's going to cross at every single one of these, and that's good because my puzzle pieces all fit together. Just a bit of a warning, my math lab can be a bit frustrating because we're not in class paying attention to how high these peaks or valleys are going. My math lab is going to want the graph to be a bit more accurate. And so what you can do is try to plug in points to the function between, like say between a -3 and a -1, you could plug in the -2. If you're getting them wrong, but you've got the shape generally and you think it's just that Y thing, go on and don't worry about it. Send me an email and say, hey, Krista, I think I got 2, 6, and 8 right. Would you go look at them? Okay? So don't spend all your time trying to find out what those Y's are, because that's really not the point. of this. And so this is one of the sections where my math hub frustrates me. It will frustrate you too. Don't worry about it. As long as you have the general shape, you have the pieces together like we're talking about right now, send me an email. I'll go back in and look at them. I may have to look at them for every one of you, 39 of you. I'm happy to do that, okay? So don't get frustrated over what we're not focusing on here in class, okay? All right. Next one, a little bit different on this one. And the reason it's different is because this one is an x squared. But really, what is that? That's like an x minus 0 squared. Okay, so it's really the same, just not explicitly writing that 0. If I were to cover the 2 and the negative 2, I'm going to get an x squared times an x times an x. Do you see it? Good. So my leading term is x to the 4th. My n is 4. My a sub n is what? It's just a 1 again. There's like a 1 out front. Since n is even and a sub n is positive, my n behaviors rise to both sides. For my x-intercepts, if x squared or x minus 0 squared equals 0, x equals 0 is your x-intercept. If x plus 2 equals 0, your x-intercept will be negative 2. Subtract 2 from both sides on that one. And if x minus 2 equals 0, add 2 to both sides. X is a positive 2. For x equals 0, what is its multiplicity? It's the 2, it's the squared. Since that's even, we're going to have a bounce at x equals 0. X equals negative 2 comes from this factor of x plus 2. Its multiplicity is a 1, which is odd, so it will cross. Same thing for x equals positive 2. It comes from x minus 2. The multiplicity is 1, which is odd, so it will also cross. So we have x-intercepts at 0, negative 2, and positive 2. So we plot those on our graph. Left end behavior rises, as does right end behavior. At negative 2, I know my multiplicity was odd, so it's going to cross. But we've still got to join our dots, and so it's got to come back up. At 0, it bounces or stays on the same side. So since it was below on the left, it stays below on the right. And then our puzzle pieces fit together because we knew it needed to cross at x equals positive 2. Any questions on that one? Great. Then you might say, well, Krista, that's all great as long as the polynomial comes in factored form. What if it doesn't come in factored form? Well, there are lots of different tools out there that are beyond the scope of this class that involve something called the rational root theorem that we're not going to talk about. But if you can have an easily factorable polynomial, then you can factor it. And so here we have x cubed minus x squared minus 20x. Just to give ourselves some more room, I'm going to write it on a separate sheet of paper. F of x is equal to x cubed minus x squared minus 20x. So last one to graph for today is this one. If we think about factoring, I see that every one of my terms has at least one factor of x in it, so I can factor 1x out. Factoring 1x out of x cubed leaves me with an x squared. Factoring 1x out of an x squared leaves me with an x. And out of the negative 20, x leaves me with the negative 20. So I've begun my factoring. Greatest common factor, factor it out. And now we have a quadratic. Let's see if we can factor it. Two values that multiply to give me x squared are x and x. We need two numbers that multiply to give me a negative 20 but add to give me a negative 1. Those will be a negative 5 and a positive 4. Negative 5 times a positive 4 is a negative 20. Negative 5 plus 4 is a negative 1. So I have factored it. Once you have your polynomial and factored form, it's no different than any of the others that we've already talked about. Okay. What's easier in this case is picking off your leading term. Your leading term is x cubed here, which you can see is exactly what we get from our fingertip method, x times x times x. My degree here is 3, which is odd. My leading coefficient is 1. The value in front of x cubed is 1, which is positive, telling my end behavior will fall to the left and rise to the right. From the factored form, that's where it's easiest to find our x-intercepts. Our function equals 0 if my first factor is an x equals 0, if x minus 5 equals 0, or if x plus 4 equals 0. X equals 0 is one x-intercept. If I add 5 to both sides, I'll get x equals 5. For the last factor, if I subtract 4 from both sides, x equals negative 4. Any questions on how we got those? Great. The multiplicities on each of these are 1. So multiplicities equals 1 for all. So it's going to cross at each one of our x-intercepts. Finishing the problem. Remember, you're going to start with graphing your x-intercepts. X equals 0, x equals 5, and x equals negative 4. From the leftmost x-intercept, it falls, and from the right, it rises. It's going to cross at each one. So since it's below on the left for x equals negative 4, it will be above. But come down to our next intercept. Since it's above on the left here, it will go below. And then the good news is it did cross again. Okay. Graphing polynomials. Not too challenging as long as you know the very few things that we've talked about today.